Alright, let's have some fun and talk about valence shell electron pair repulsion theory. This is one of the places chemistry gets kind of pretty. Um, there's lots of beautiful chemistry, but this is fun just in theory to go over molecule shapes and get to problem solve and have some fun with something that's sort of challenging. So first of all, this is a theory meant to explain the observations we see. This is that most of chemistry is beyond the scope of what an eye can see. So we have to use a theory to substitute for what that is. So this theory allows us to use electron structures, dot structures, to determine molecular shapes. The structure around a given atom is determined primarily by minimizing repulsions. And that's why it's electron pair repulsion. Remember, we have like charged, negatively charged objects in space, and they're going to exert force against one another and repel. Both bonding pairs of electrons and pairs of electrons, which we learned are electrons that are internuclear, where we have a nucleus here and a nucleus here. Most electrons that are in a bond are going to spend time in this space. Very little time out here, lots of time here. Okay, so those electrons in between two bodies are going to spend most of their time in this space, and that's a bonding pair of electrons. Electrons that aren't bonding, say they are in this window of space here, are going to exert a force also, but it's a different kind of force. It's not exactly the same. And so a non-bonding pair of electrons would be not in internuclear space, but on the outside, the periphery of one of the atoms involved in the structure. So we are basically minimizing repulsions in our drawings. So the first trick to this is we're going to use our Lewis structure skills to get the rough idea of what we have, and then we're going to count electron domains. Electron domains means any effective electron pair. It can be a lone pair, a non-bonding pair of electrons, or electrons in a bonding domain. 2, 4, or 6 electrons in a bond count as one electron domain. So we're looking for either kind, a lone pair of electrons or bonding electrons, and the goal then becomes to decide how many we have and then geometrically put them as far apart as we possibly can. Now, what we have to remember, that was discussed a little bit already, is that a non-bonding pair of electrons being closer to the atom, in this case a central atom in a molecule, like water for example, oops, that's supposed to be an O, these non-bonding pairs of electrons are going to exert a greater downward force on this bond angle than do the pairs of electrons in the bonds of methane. Okay? Now there are also atomic property differences from carbon to oxygen, but for the purposes of this understanding, this is going to create an angle of about 109.5, where this pairs of electrons are exerting a slightly greater downward force on these two bonding pairs of electrons, shrink this angle down to about 104 for water. So it's a subtle difference, and as far as the AP course goes, you don't need to memorize 104. Just know that when you have pairs of electrons, you will shrink the expected angle a little bit, and so you can just say this for the bond angle for anytime you see a pair of electrons exerting a force instead of a bond. So let's get started. The first shape we're going to talk about, and you do not need to memorize the root shape, AX2. It just, A is your central atom, X are peripheral atoms. That's it. When we see electron pairs, we'll have an E out here. But our first example is just two bonds and one central atom. So we're going to do beryllium difluoride because we haven't yet. And you might say, but that's an ionic compound. Beryllium, yes, it's a metal, but its electronegative behavior actually has a lot of covalent character, and so we're going to draw this as a covalent compound. So we have from beryllium, we have 2 valence electrons, and then from each fluorine, we have 7, so that's 16 valence electrons. So when I draw, I'm going to singly bind each fluorine, and I've used 4, 6, 8, 10, 12, 14, 16. And keep in mind, beryllium is one of the atoms that is stable with fewer than 8 electrons, and so we see that this is actually the stable structure for beryllium difluoride. So we see that we have 2 bonded atoms. We have, in this drawing, a symmetry. And so not only is this a linear molecule, it has a 180-degree bond angle, and then it's also going to be nonpolar. Okay? So nonpolar because it's got this linear property. Now, this being an ionic compound, that kind of goes out the window. But the drawing as it is nonpolar. We see a symmetry about the bond. Two of the same atom, bond properties are the same, and they are perfectly linear. So here we go, AX2E. We have a pair of electrons added on now. This is going to be an electron domain geometry is going to be trigonal planar, and then molecule geometry, ignoring the pair of electrons, is the bent shape. So this is where we have 2 bonds and 1 lone pair. So let's do sulfur dioxide. In sulfur dioxide, we have 18 valence electrons to work with. So we're going to central sulfur, single bond each oxygen. 4, 6, 8, 10, 12, 14, 16, 18. And we have an issue there with sulfur, so we're going to need to take an electron pair from oxygen, either one, doesn't matter which, and form a double bond here. What you're going to notice here is there's no real easy way to get rid of the formal charges. Oh no, there is on this one. So we have a now we have a 1, 2, 3, 4, 5, a +1 charge here and a -1 charge here. And we can stabilize because sulfur can support more than 8 electrons in bonds, so we can go ahead and do the double bond again and stabilize our sulfur dioxide molecule and get rid of our formal charges. Now, if this were nitrogen, we couldn't do it, but since it's sulfur, we can. Here we go. And now we have the octet met for all. Sulfur's got 2 extra electrons, but it's okay if it does. The oxygens have 0 formal charge. The sulfur has 0 formal charge. 1, 2, 3, 4, 5, 6. So what we see is we have 2 bonds and 2 pairs of electrons. Now, a double bond is a bonding domain. Okay, it doesn't count as 2 bonding domains. It's just 1. So we have 2 bonding domains and we have 1 electron pair, and this is the bent shape. Now, since it's a bent shape with an electron pair, this would certainly be a polar molecule. We see that you're probably going to be nonpolar in the bond sense, maybe a little bit polar in the direction of oxygen, but the electron pair on the central atom provides some asymmetry, making this a polar molecule. Next, we have AX3. So we're going to real quickly draw boron trifluoride. We have 3 + 21, 24 electrons. And boron is another one of those atoms that is okay if it does not quite have 8 electrons. It is steady stable with simply 6. It does interact with things that have free pairs of electrons as an electron pair acceptor, but in this case we're just concerned with the drawing itself. This is a nonpolar molecule. It's trigonal planar, which means it's flat in one plane like a Dorito. Well, at least a well-formed Dorito, not one of your curly Q Doritos, with a bond angle of about 120 degrees. Sulfur trioxide, you're going to find if you draw, will have 3 double bonds, which is a pretty interesting structure. The next example, we have AX2E2. This is our water drawing, 2 pairs of electrons. We'll do oxygen difluoride for fun since it's something different. We have 20 electrons to draw here. We've drawn 4, 6, 8, 10, 12, 14, 16, with 4 left over to the central atom. And we definitely have a large degree of polarity here because of the pairs of electrons, and we have a little bit polarity in the direction of fluorine because it's more electronegative, but the polarity in this molecule comes from unshared pairs of electrons on the central atom providing asymmetry. Because these pair of electrons are on the central atom, we are less than 109.5 degree bond angle. It's tetrahedral in its electron pair geometry, 4 electron domains, and then bent in structure, similar to the last example. AX3E. So this is our 3 bonds, 1 pair of electrons, and ammonia is the primary example we'll deal with here. In ammonia, you've got 8 electrons, and here are 6, and then 7, 8. So ammonia is another polar molecule because we have asymmetry about the central atom. We have a pair of electrons and a polar bonds in the direction of nitrogen because it's more electronegative than hydrogen. Since there are 4 electron domains, it's tetrahedral. The shape you find is trigonal pyramidal. So it's pyramidal here. The electron pair forces this bond angle down to a little bit less than 109.5, and that's ammonia. AX4, this is the methane example, tetrahedral. We have, in this case, again, 8 electrons. Let me draw this in a way that I see people make a mistake. People draw this often in this beautiful square shape, and then I ask them this bond angle, and they put 90 degrees. We have to think about these objects we're drawing. When we go from Lewis structure to valence shell electron pair repulsion theory, we need to go from thinking about this in terms of our flat drawing to our three-dimensional space-occupying molecule. Okay, 4 electron domains will have a root bond angle of 109.5, always. Since there's no electron pairs, we can say with confidence the average bond angle is going to be 109.5. Of course, this fluctuates and changes all the time in a real molecule. It's vibrating, stretching, moving around with the forces around it, but the average bond angle is about 109.5. Tetrahedral in terms of electron domain geometry, tetrahedral in terms of shape. Next, we have AX2E3. And this is one of my favorite because we got 5 electron domains, lots of action, and we have 2 fun examples of Xenon difluoride. We'll go ahead and do that one first, and then we'll just look at the drawing. Xenon's got 8 electrons, each fluorine's got 7, so we've got 14 plus 8, 22 electrons to care for. So I'm going to bind my fluorines. I'm going to use 4, 8, 10, 12, sorry, 4, 6, 8, 10, 12, 14, 16. I said that we had how many pairs of electrons? Sorry, how many electrons we had? 8 and 14. So that's 22. We've used 16 so far, so we have to put 2, 4, 6 on the central atom. 3 pairs of electrons about the central atom, and then 2 fluorine atoms on either end. This is, believe it or not, a nonpolar molecule. Okay, nonpolar because we have symmetry about the central atom with the electron pairs, and we have symmetry about the bond with 2 fluorines. Now, if for some reason one of these were chlorine and fluorine, then you would probably have a degree of polarity. But since you have identical atoms, we have a nonpolar molecule. I do want to go back real quick on methane. I didn't mention this is a nonpolar molecule. One way you can quickly make methane polar is to make it this molecule. We have hydrogen, hydrogen. Oh, look at chlorine. In this molecule, we have polarity because we don't have symmetry around the central atom. Very similar to methane, but a polar molecule. Okay, so let's get into AX3E2, chlorine trifluoride. This one is in our practice set, but it's a fun one. We have 28 electrons to care for here, so let's draw them out. We've drawn 6, 8, 10, oh, sorry, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, how many did we say we had? We had 28. So we have 4 electrons on the central atom. This ends up being what's called a T-shaped. I neglected to mention the electron pair geometry on the last slide, but it's anything with 5 electron domains is trigonal bipyramidal in terms of electron domain structure. This one, we have 2 electron pairs around the central atom, and then we end up with a T-shape, where we have roughly this flat T here. The bond angles here, this should be actually less than 180, but not terribly important. That usually doesn't get asked very often. I'm not going to ask it. What I need you to understand here is this is an asymmetry in this molecule, so it is polar. The T-shaped structure is kind of interesting, but what we're doing is minimizing repulsions. And because electron pairs because electron pairs are so repulsive, this is the configuration we tend to see them take on. So we have polar, we have 3 bonds and 2 pairs of electrons, T-shape. Let's talk now about AX4E1, sulfur tetrafluoride. Sulfur tetrafluoride, we have 6 and 28 for 34 valence electrons. And so when we draw our structure, we're going to first start with what looks to be a pretty typical structure. But what we're going to find is when we attempt to draw it, we've used 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we have 2 extra. They'll just go on the central atom in a pair. And that's going to give us 5 bonds, 1 pair of electrons, give us a fair degree of asymmetry for a polar molecule. regardless of what's on it, this is going to be polar. Trigonal bipyramidal in terms of electron pair geometry. Seesaw is what we call this shape, because we sort of have this axis that acts like a fulcrum here, these 2 feet, and then a seesaw, pair of electrons on top. Bond angles, this is correct, less than 120 and 90 degrees. Next, AX5. PCl5 is a fun one. This is one of that first one where we kind of experience an expanded octet in terms of atom binding. And we ask ourselves, is this okay? And yeah, it sure it is. Phosphorus is large enough to support more than 8 electrons and still meet its own needs, as sharing 5 electrons. So this is that structure. You have 40 electrons shared here. And this is a nonpolar structure, provided that all these atoms are identical. We have bond angles of 120 degrees around the central atom and 90 degrees between the polar atoms and the 3 around the center. Trigonal bipyramidal for both. Finally, we have the octahedral structure. That's a mistake. Ignore that. Let's go to this one. AX4E2 is another fun one. We have Xenon Tetrafluoride. We have our noble gases not behaving nobly. They're mixing with the common atoms here. So it's very modern royals, I guess, right? So we have 4 bonds, 2 pairs of electrons. We call the electron pair geometry, electron domain geometry, for when there are 6 electron domains. It's called octahedral. This particular shape will be called square planar, and this is minimizing repulsive forces again. So you can examine this structure. This is actually in your textbook as well. Bond angles will end up being 90 degrees, but let's draw it. We have xenon and tetrafluoride. We have 36 electrons to care for here. 8 from xenon, 28 from fluorine. So here we go. Oops, I'm going to get a line there. That's an ugly bond, but it'll do. So we've used 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We said we had 36, so there's still room for 2 pairs of electrons on the central atom. And so what this exploration here shows you in the diagram is that we experiment by putting electrons in all possible domains. And what we find experimentally is the shape that wins is this square planar shape for minimizing repulsions. Again, the electron pairs are going to repel maximally, and they tend to win because they exert a greater force because they're closer to the xenon atom than these bonded electron pairs that are spending time in the internuclear space. So while it looks bigger, these electrons are actually probably a lot closer to the xenon atom than the bonded electrons in fluorine. So they exert a greater force against each other, and so they're going to repel maximally. We have a nonpolar molecule as it's written here, and that's because of this structure. The electron pairs are diametrically opposed, and our fluorine are about the center of the atom, and they're equal forces in opposite directions. So interesting nonpolar molecule, pardon me. AX5E1, iodine pentafluoride. So we have 7 times 6, 42 electrons here. There's our iodine. 3, 4, 5. And we made fluorine the peripheral atom a lot in this, I guess. So when we do this, we're going to have 40 electrons used. You know, like I said, we have 42 electrons to draw. So let's take a look here. So we've used 40 electrons. We have 42 electrons to use. That means, again, 2 electrons are around the central atom. This is going to be a polar molecule by default. There's no way to make this nonpolar because you have an imbalance of forces. 6 electron domains. Octahedral, again, is 6 electron domains. This particular shape is called square pyramid. If you were to connect the dots, you'd have a square pyramid. The angles are 90 and less than 90. This electron pair is going to force these upwards, so the downward angle here is a little less than 90, but about the center it's about 90 degrees. And then finally we have AX6, when we have 6 electrons around the central atom, and my diagram is wrong. It's not IF5. So let's make up a model atom. We have, let's do sulfur hexafluoride. This is fun stuff. This is the deep voice gas. And we have 6 plus 42 electrons, so that's 48 electrons to care for. 5, 6, 1, 2, 3, 4, 5, 6. And by now we're probably pretty used to, so I'm just going to put a hat on each one of these, and that's going to be 8 electrons. And just to make this, do not do this on your test. This is just to simplify the drawing. We know we had 48 electrons to use, and we have 6 plus 2, 8 per fluorine, so that's going to be 6 times 8, 48 electrons used, no extra electrons. This is a nonpolar molecule. This deep voice gas, if you've never seen it before, actually is much more dense than air, can be poured. It's a clear, colorless, odorless gas. You can pour it into a fish tank and float a foil boat on it. And so if you ever get a hold of some, bring it to me. I want to play with it. I hope this has been helpful to you. Please see me in class if you have questions about valence shell electron pair repulsion. We need to discuss the polarity of molecules as we draw them, and I hope you come with great questions.